We're now ready to solve a problem with binary search trees, given your knowledge that you've just discovered. Now, each of these problems in the modules are an exercise for you to apply your knowledge to this particular problem that I introduce. For each of these problems, I will have full code worked out that you can look at afterwards, and in fact, I'll have a small narrated section of this video going over the code. But I encourage you to try out the problem on your own, at least think your way through it a little bit to see how you would solve the problem. So let's begin. We've mentioned the difficulty with the binary search tree in that it can quickly become out of balance through repeated insertions and deletions. And this means that when I start with a binary search tree that's empty and I want to add a bunch of elements to it, I always have to be careful about how I insert those elements. But there's an interesting problem where if I already have a sorted array, which I could get from a file or the user gives to me, and I want to create a binary search tree from that sorted file, the obvious solution will be the exact wrong thing. If I insert the elements into the binary search tree in sorted order, 1, then 2, then 3, I would obviously create a binary search tree that's skewed to the right, and in fact will have not a good structure. It will in fact look just like a long linear linked list. So the question is, given a sorted collection, can I create a balanced binary search tree from the beginning and do so without much effort? And so I want to give you some ideas about how you would go about doing this. Here's my sample binary tree that I've used throughout. And if you look at that containing those 7 values, observe that the root, which is 7, is in fact the median of the elements in that collection. And then look further. Its first child, 5, is in fact the median of the left part of the array. And its right child, 10, is the median of the right subarray. And if I reflect on this a little bit, you might be able to see a way to insert the values into the binary search tree in that order, level by level at a time. If I first insert 7, and then I insert 5, and then 10, and then insert 2, 6, 8, 12, I will create a balanced binary tree. And that's the structure that I want to be able to find a way to do so in Python. And what's nice is, with a very small, elegant recursive function, you can take a sorted collection and create a balanced binary search tree from scratch. So now I'll show you the solution to creating a balanced binary search tree given a sorted collection as your input. If I have a ordered collection here, and I'm going to use the binary tree that I'm importing from that BST module that we just created, what I want to do is I want to consider this as a recursive problem. And it's very similar to what the binary array search was. In the binary array search, as you know, you were trying to search for a target element inside of a range from low up until high. And you were repeatedly cutting the problem in half each time and exercising just one subproblem. But here, I'm going to break the problem in half each time, and I'll exercise 2 subproblems. So I want to insert the median value, and then I want to insert the median value of the left subarray, and then on the right subarray. And if I repeat that process recursively, you should see that it gives you the desired results. So let's look at the code. I start with an empty binary tree. And given an ordered array, or ordered list in Python that is, I know it's ordered from index position 0 up until the length of that list minus 1. I'm going to call add range, which will presumably add all the elements of that range into the binary tree. As long as there is a range to add, that means that the low is less than or equal to high, I want to find the midpoint of that range. And that midpoint will be the median value of the range because that's the definition of median. That element in a sorted list of which half the elements are smaller and half are bigger. Once I know what that median value is, I add that to the binary tree. And then I recursively add the left range, which is from low up to mid minus 1, and then I add the right range, which is from mid plus 1 up to high. And so this is the exact same recursive structure that you would have seen for the binary array search, and here I'm putting a nice twist on it to create a balanced binary tree. So let's demonstrate this code as it runs. I'm going to start with a range of numbers that are sorted already, 0 to 9. I'm going to create a balanced binary tree using this. Now, I know that this is going to be sorted, or actually, I know that this binary tree will be balanced because I started with that sorted collection. I called the recursive function that you see there. And you can see that the root node is, in fact, the value which is the median of the left and the right. Let me look at the root's left child and the value that he has. It's this one here, which is a median of these. The numbers are slightly off naturally because 10 is not a power of 2, but you can get the gist as you look at these values, is that each time the root value is in fact an element in the middle of that subarray, and then the rest will fall out naturally. So this is the solution, a rather short and elegant solution to the problem that now should demonstrate to you that if you already have a collection of elements that are sorted, you can quickly create a binary search tree from those and then use it to great effect for the efficient operations contains as well as insert and delete.